The Electron-Ion Collider, EIC, offers a unique opportunity to search for new physics beyond the Standard Model, SM, through its high center of mass energy and coherent interactions of large nuclei. This work examines the potential of the EIC to discover or constrain light-weakly interacting vector bosons from various models through clean displaced vertex signals. The authors consider models where a light boson can be produced and identified through displaced decay vertices at the EIC. They focus on three representative models: a standard dark photon, a gauge boson coupled to the BL symmetry of the SM, and leptophilic gauge bosons that couple to lepton flavor number. The EIC's high center of mass energy and coherent scattering from large nuclei provide a marked advantage in searching for new physics, particularly when combined with the expected integrated luminosity of 100 Fb/1a. The authors propose a search strategy involving the production of a massive light vector boson A through ultraperipheral production, which can decay into an electron-positron pair with a displaced vertex. They calculate the total cross-section for this process, taking into account the EIC's electron detection capabilities and the nuclear form factor of the gold nucleus. The probability of a displaced decay is determined by the lifetime of the A, which depends on the various charges of SM particles under U(1)A. The authors also discuss the detector capabilities required to identify displaced vertices. They refer to the design document for the EK detector, which provides resolutions for the 2D distance of closest approach, dCA2D, of pions. Assuming a similar resolution for electrons, they determine the minimum distance dmin that the A must travel before decaying. They also consider a scenario with a far backward detector capable of tracking electrons with 6 less than 8 less than 4, which would improve the reach of the search. The signal selection criteria involve identifying an electron and positron each displaced from the primary vertex. The corresponding cross-section for signal events is calculated, taking into account the probability of a displaced decay and the branching fraction into electron-positron pairs. The authors conclude that the EIC has the potential to discover or constrain light-weakly interacting vector bosons, particularly if far backward particle identification capabilities are included in the detector complex. The research discusses the prospects of placing limits on the coupling strength of various hypothetical gauge bosons at the Electron-Ion Collider, EIC. The focus is on dark photons, U(1)B-L vector gauge bosons, and leptophilic gauge bosons. For dark photons, the study explores the kinetic mixing parameter epsilon and its relation to the gauge coupling Ga. The EIC's projected constraints on epsilon and Ga are presented, showing significant new bounds compared to existing limits. The discussion also covers U(1)B-L gauge bosons and leptophilic gauge bosons, highlighting the importance of these searches in understanding beyond the Standard Model physics. The EIC's potential in improving these bounds is emphasized, particularly with the addition of a far backward detector. The summaries of pages 3 and 4 detail the mathematical derivations, experimental handles, and the significance of these searches in the context of dark matter and beyond the Standard Model physics. Here is a combined summary of the 2 pages. The authors explore the potential of the future Electron-Ion Collider, EIC, to probe light-hidden vector bosons with masses in the range of a few MeV to 0.1 JeV and couplings weaker than 1 to Standard Model, SM, fields. They consider various scenarios, including the dark photon, BL, and leptophilic gauge bosons. The EIC's capabilities are shown to provide significant reach for unexplored values of the coupling strength, particularly with the addition of far backward particle detection capabilities. The analysis focuses on a clean and essentially background-free regime of parameters where the produced vector bosons have sufficiently long lifetimes, leading to displaced decay vertices in the detector. With realistic integrated luminosity allocations, coupling parameters down to tilde operator 5 × 10⁻⁶ can be probed. The addition of far backward particle detection capabilities can push the reach down to couplings tilde operator 10⁻⁶ and up to masses Ma tilde operator 500 MeV. The authors also discuss the importance of muon detection capability at the EIC, which could provide additional statistics and strengthen bounds on searches for beyond the standard model, BSM, particles. The EIC's capability to collide polarized electrons with ions can also give an additional handle to probe the chiral structure of the A couplings, which is not commonly featured in most current and future experiments. The paper provides a comprehensive review of previous and current experimental searches for light-hidden vector bosons, including beamdump experiments, fixed target experiments, and collider searches. The authors also acknowledge the limitations of their study, including the assumption of excellent electron final state identification capabilities and the neglect of the EIC electron beam polarization. The appendix provides a detailed calculation of the differential cross-section and signal for the process, including the polarization and spin-averaged squared amplitude, and the definitions of the Mandelstam variables. Here is a combined summary of pages 7 and 8 of the research paper. The paper derives the ion frame production cross-section for a hidden vector boson, A, in the context of the Electron-Ion Collider, EIC. The cross-section is expressed in terms of the squared amplitude, A squared, which is a function of various kinematic variables, including the energy of the initial state electron, E, and the energy of the vector boson, E_k. The authors also introduce the lab frame variables, such as the energy of the initial state electron, E_lab_E, and the energy of the ion, E_lab_ion. The paper then proceeds to integrate the cross-section in the lab frame, which is more useful for experimental purposes. The authors derive equations for the zeroth component of the vector boson's formomentum, x_E, and the quotient of the third and first components, tan theta_k. They also obtain the Jacobian determinant of the transformation from x cos theta_k to gamma_lab_k, eta_lab_k, which is necessary for the integration. The decay width of the hidden vector boson, gamma_A, is also calculated, taking into account various decay channels, including neutrino, charged fermion, and hadronic decays. The authors use the experimentally determined ratio to estimate the hadronic decay width. In the context of the EIC, the authors discuss the concept of distance of closest approach, DCA, for particles produced in displaced decays, such as the lepton pairs in their process. They define the transverse DCA, DCA_2D, and relate it to the kinematic properties of the dark boson. The authors assume a straight-line trajectory for the leptons and estimate the DCA using the angle of the lepton with respect to the vector boson. They also derive equations for the transverse DCA, taking into account the polar angle phi of the leptons. Overall, this section of the paper provides a detailed calculation of the production cross-section and decay width of the hidden vector boson, as well as an analysis of the DCA for particles produced in displaced decays. Here is the combined summary. The angle theta LL, which characterizes the dark photon's decay, can be related to the boost gamma through formomentum conservation, as expressed in equations B7 and B8. These equations describe the conservation of energy and momentum in the decay process. By solving for sin theta LL, we arrive at equation B9, which approximates the sign of the angle theta LL in terms of the boost gamma, the masses of the dark photon and the electron, and the velocity versus. The approximation in equation B9 holds because the mass of the electron is much smaller than that of the dark photon in this study. This expression for sin theta LL is crucial in determining the minimum resolvable value of transverse distance of closest approach, DCA, for particles at the Electron-Ion Collider, EIC. According to previous studies, the minimum resolvable transverse DCA is approximately 100 micrometers. Using this value, we can calculate the minimum distance the dark photon can travel before being considered displaced, denoted by dmin, as shown in equation B10. This distance is dependent on the boost gamma, velocity v, and the laboratory frame angle theta lab. The calculation of dmin is essential in understanding the decay properties of dark photons and their potential detection at the EIC. The table on page 10 presents the results of the dark photon search at the EIC, with various benchmark points and their corresponding dark photon masses, couplings, and branching ratios. The branching ratios are calculated assuming the dark photon decays primarily into electron-positron pairs. The table highlights the regions of parameter space that can be probed by the EIC, providing valuable insights into the potential discovery of dark photons.